important to determine the significance of your results. So you're not just like reporting false conclusions. You can say, for sure that your results are significant and all that stuff.
So patterns and relationships that we see have meaning.
Yes.
What are humans prone to? And what are we really good at? And it's
meaning in
what's
something.
that, Tristan?
Seeing meaning in something random.
Oh, we are absolutely spectacular at finding meaning in random patterns. And we do it everywhere. If you've ever just sat, and I'm now looking out my window, with your head back, staring up into the sky on a cloudy day with cumulus clouds in the air, what do you start to see?
Animals.
Maybe you see animals. What does someone else see? Mitch, what do you see, buddy?
Like state or something.
What's that again?
Like states or whatever.
Oh, you see states. You see state outlines. Like I see Georgia here. And over here, I see Florida. I like that. That is not an answer I expected. That is excellent. Tristan, what do you see, man?
One time I looked in the sky and I saw what I could swear was a frog, and I could see it extend its legs as it jumped across the sky.
Absolutely. We see patterns. I see the Imperial Starship from Star Wars. That is the pattern I almost always find somewhere. That first image from Star Wars back in the 70s still seared into my head. And I see that everywhere. It's not that the clouds are random. There are actually very predictable ways to why they form in the shape they make. But what we prescribe on top of that, that can be random. And we're incredibly gifted at seeing random patterns. And there's good evolutionary reason for why we should see patterns in random events. Because the cost of failing to see a pattern is very low. I'm sorry, let me rephrase that. The cost of seeing a random pattern is very low. But the cost of failing to see an obscure pattern can be incredibly high. And you can think about it like maybe just the noise in a bush and just ignoring it as a random pattern. Well, most of the time, that's okay. But if that's a lion, that's a big problem. Because if you fail to respond to patterns, when those patterns can be real, is a real issue. Now, the trouble with that is we deceive ourselves way, way too often in assuming something is actually occurring when it's not. And that is one of the major benefits of statistics. It controls us from our tendencies to see patterns that do not exist. And it forces us to sort of substantiate and justify the patterns that we wish to describe. Now, the figures I gave you, they're totally appropriate statistics. They're just frequency figures, straightforward, describing the number of events relative to days. Each of them provides really important information. The information that's provided is absolutely accurate. It may or may not be complete, depending on what you want to define as COVID, but they're very accurate. But in each case, they provide some type of information, and they sort of, as a result, do not provide other types of information. So I ask you guys that. And Casey, maybe you can start us. If you could start us with number of cases by day. That figure, the yellow one in the top left-hand corner. What does that tell us?
So what I got from it is the amount of cases that were being tested for that week. So in like the beginning of July, there were 80,000 new cases of COVID. But
okay,
then,
so you're looking at the figure on the right-hand side. Per week. That's fine. Let's go for that. So describe the cases by week, and what does that actually tell us?
I think that it just tells us how many people are getting sick right now, how many people are being exposed, or like how many people have like a chance of being at risk for it, just the amount of people being tested.
Okay, so it might actually inform all those other pieces. It might tell us about how many people are being tested. That's true. It might tell us about the overall risk. That is true. Or it might give us some indication about the number being tested and the overall risk. But exactly what does it say? Because it doesn't actually say those pieces of information. It doesn't give us that information. So Alana, do I have you?
Sam, can you jump in?
I'm sorry, what was that? I'm not sure.
Can you hear me?
I can.
So what is it called? So you wanted me to tell you what they're like explicitly telling you?
Narrowly define what is it telling us?
Well, the yellow one is it's cases, it's the number of cases per day. The red, what is it called? Like the one in the middle shows us like that
Let's not
the
worry about
deaths,
that one yet.
what is it
Let's
called?
just deal with the one in yellow. Perfect. So in contrast to the one Casey talked about, the one on the left-hand side, the yellow one tells us the number of cases per day. And just per day. Now, Alexander, are these the same figures?
You're saying between the left side and the right side?
Between the left side right here, the yellow one, cases per day, and the right side over here, the cases per week.
Well, the one on the left is cases by day, one is by week. So one of them's just spread out a little more, but they're basically the same figures.
So that's kind of an interesting thing. They're the exact same data. So now we have the most difficult question here so far. Tara, and you're up on it. They use the exact same data. The difference is they represent them in different scales. Why do we need both? What do we get by having both that we would be limited by if we only used one?
Tara's audio's down today, just today, but I think she's gonna type it in the chat.
Okay, let me see if we get that. Okay, thank you. Got that. Appreciate it. Okay, so Tara brings up the point that, and she's now going down to the deaths. And we're not talking about the deaths yet, but let's address that point. She's bringing up the point that there is the potential for reporting errors that may be associated with different issues. And do we get that information from these figures? Not at all. In fact, I think that's a really good observation in the sense of where statistics are so incredibly valuable and what statistics don't necessarily tell us. What statistics are telling us in these cases are two very simple things. How many deaths have been reported? And the quality of that information is as good as the information that we receive. So, as an example, in the state of Florida, only those cases where it has been certified on the death record as associated with COVID-19 are reported. CDC guidelines encourage states to report anything that is likely COVID. But in the state of Florida, we don't report those. We ignore those altogether. So the CDC numbers would be higher than what the state is providing. Now, what Tara is speaking to is a potential conflict of interest in terms of how numbers are being reported and if there is a desire for extra reporting as a result of resources, funding. That's all great. But on this figure, do we see that information at all? Is there anything in these figures, in these stats, which tell us about why we might have a particular rate? Is there anything in these figures that tell us the factors that are influencing these rates? Is there anything in these figures that are telling us how these rates are being reported?
No.
None of it. And that is, and by the way, this is a beautiful exercise because this speaks to one of the most difficult things about stats. Stats gives us the best information we can have to make decisions. But one of the things that you have to learn is to take the information for what it is saying and then separately deal with the interpretation and deal with the next set of questions that might go on. These are two separate exercises. The first is describing the pattern. The second is making the interpretation. More than 90% of what we're going to be doing in this class is describing the pattern. We'll leave the interpretation for a different stage of the scientific understanding. Does that make sense? Questions?
So would you say that as humans, you say we see patterns and we on a daily, or would you say as humans we fail in the interpretation of patterns? And one example I'm going to give you is that a few years ago I learned that like 90% of like persons who do trading fail, and trading is just analyzing group psychology, which is just patterns on a screen. But I always wonder why over 90% of those who do this fail. So that's why I asked this question.
It's a good question. It actually is a central question in economic theory, where economists assume rational decisions. But just ask yourself in your basic interactions, do you behave rationally all the time? And I can't speak for you, I can speak for myself. No, I don't. You know, even to the type of science that I do the type of science I do because I like the topic and I like the ideas. I married the woman that I did, not because I gave a pie chart that sort of described her overall relative strengths in different areas, but there was an eventual decision that was, you know, I describe as irrational. She says, no, there were a lot of good reasons that you married me. That essentially brought us together. When we make trading decisions, we try to use evidence, we try to use ideas, but a lot of it is based on personal beliefs and ideas that may be independent of that evidence. Our job as scientists.
So you believe that personal belief? My bad.
No. Our job as scientists is to use the evidence and then describe relative to the evidence. So here is some information about you guys. These are your majors. How do you describe the overall pattern? What do you guys notice?
Most of us are biology majors.
A Bachelor of Science in Biology.
Yep. Bachelor of Science in Biology rules in this class. There's some, you know, biology, there's 2 environmental science, there's a little bit of biotechnology, and then the integrated studies. Love it having you. Thank you for being here. That's awesome. But yeah, we are biologists, straight up to the core. How about academic year? What do we notice?
Most seniors.
Yeah, we tend to be a little bit biased towards seniors and juniors. You know, you take upper level students, and that's primarily where we're at. There are a few sophomores and there are a few graduate students, but we are generally, as a class, upper level students. How about career and educational goals?
Most people want to go into a medical field. Well, not most, but a large portion of us.
Riley, I think that was a good catch too, buddy. That was well done. So technically, most do not want to go to medical school. Most people want to do something else. But the plurality do want to go to medical school. Great observation. What else do you notice here?
Aside from those wanting to go to medical school, it's pretty diverse.
There's a lot of variation. You know, there's a lot of different ways that people are thinking about their lives and their career, which is, I think, excellent. That is good because that means we'll have different types of insights as we go through the semester. This is the first time I ever built this figure. I found this fascinating. These are the courses that you all defined as being important for being successful in this class. And I'm going to start with Easy. What do you see? What do you notice?
A lot of people chose biology, 1 and 2.
Yeah. Yeah. The plurality, in fact, in this case, you can't see it from this figure, but I can tell you individually, the majority of people identified Bio 1, almost everybody, and almost everybody identified Bio 2. That's a great observation. Astrid, what else do you see?
Statistical methods for sure is another one.
Statistical methods. I love that. But Dakota Rivers, I'm going to come to you back on that statistical methods. You notice anything kind of funny about statistical methods in comparison to Bio 1 and Bio 2?
Yeah, that was the first thing I noticed, was that it was a much smaller percentage than both Bio 1 and Bio 2.
Yeah. Statistics barely broke half. So barely half of you all thought statistics was important for being successful in this class. I don't know what to make of that, except it made me giggle. So that was, yeah. Does anyone have a thought? Like, what's going on there?
I think a lot of people probably did classes they took. And like, we've all taken Bio 1 and Bio 2 for sure. But a lot of us haven't taken differential equations or physical oceanography. So I know that's like implying calls to the data.
True. No, that's a great observation. But everyone's taken stats, presumably if you're an upper level student. And that made me giggle. The fact that stats was barely identified by a majority of you.
I think you specified in the college level, so maybe they had taken it in high school and the credits transferred.
That's clever. That's a good observation. That's interesting. What you're doing here, and both Tristan and Kayla are doing this, is really good science. So we don't come to conclusions based on what we see in the statistics. Instead, that generates other ideas and other ideas that can be tested. So that is a good way to sort of think about stats. We see patterns, we can describe those patterns, and then we use that to inform what we want to then do and what additional things need to be looked at. Isaac, last thing, do you notice any other patterns here?
Just that there's a lot of people who've taken just random outlier courses that I guess the question was kind of broad, so I mean, I put down just all the sciences I took, so I'm assuming that's what most people did as well.
That's actually a really interesting observation, Isaac. There were 3 or 4 people who put down a very long string of courses, kind of anything they did in science. But that was only 3 or 4. I would say maybe about a third of people put down maybe just 1 or 2 courses and then moved on. So the question was broad, and for this type of questions, I like broad. But there was a lot of variation in what people were thinking about would be influencing their development. In one way, I imagine these are courses that had positive impacts on you, and therefore they still kind of carry through. But that's another hypothesis that can be easily tested. So, this is called a paired figure. Let me walk you through this a bit. So, these are box and whisker plots, and we'll talk about these in detail later in the semester. The bold dark line in the middle, that's the median. This represents the interquartile range. Another way of thinking about that is 50% of respondents are within this range. This reflects 1.5 times interquartile range. Another way of thinking about that is this is the range of your data set. So this is where the middle population lies, and this is where sort of the rest of the variation exists. And you can see these box and whisker plots for statistical intuition, where this is your self-perception score. This is where you said how confident you were in terms of statistical intuition, where 0 would mean you have no confidence in terms of your statistical intuition, and 100 means that you are 100% confident. You are a rock star statistical intuition. Make sense? And then this is your research skill, where again, a 0 would mean that you have no confidence whatever in your ability to do research, and 100 would mean that you have full confidence in your ability to do research. What you're looking at here are paired individuals. So each one of these dots represents one of you. And the lines represents the difference between your statistical intuition, your self-perception of your stats, relative to your self-perception of your research. In cases where the line goes up, that means that you are more confident about your research than your statistical intuition. In cases where the line goes down, that means you are more confident about your statistical intuition than you were your research. And in cases where the line is perfectly flat, that means that you are even. These figures have a lot to unpack. And Bertilla, do I see you?
Yes. So
You want to give a first pass?
there are a lot of people who have better research skill than statistical intuition, as I see more lines that go up.
So that's two things. So let's unpack one of those at a time. So this is not your ability, this is the perception of your ability. So yeah, you think you are more confident about your research than your statistics. And then go ahead, hit us with that second piece.
And then I see more lines going up. So, and I see only 3 that are pretty much the same.
Okay, so good. Most people are going up. So most of you are more confident about your research and your stats, but there are a few people who are going down. That's excellent. Okay, Courtney, you get the more difficult question. What else do you notice? And this is not about interpretation. This is just about the pattern. What else do you notice?
That most people know how to like apply their statistics to their research, maybe.
That's an interpretation. And we will talk about those once we have a little bit more information about the stats. But right now, I just want you to describe the pattern. Don't worry, you got the tougher assignment.
That people probably have like more research skills.
Oh, that's interesting.
Than that they have statistical intuition.
That's again an interpretation, but let's play with that. Maybe one explanation, since we were going to use a hypothesis, is that you've had more experience doing research. And as biologists and environmental scientists, you presumably have done some research in your classes. You've definitely done canned lab experiments, but maybe you've actually done some research in the classes as well. Or maybe you're also doing research outside. That's great. But now I'm going to keep it really strict. Next person, Madeline. No interpretation, just description of pattern.
So what I've seen is that there is a larger range with statistical intuition there is with research skill.
I think that's a very good observation. There is more variation in terms of your perception, your statistical intuition versus research skills. Those are great. Those are really good descriptions of the overall pattern. So, this. What we're looking at here is we are looking at your self-perception. So this is a perception of your statistical intuition, where people down on the left-hand side, you are not confident about your statistics. People on the right-hand side, you are very confident about your statistics. And then on the left, we have research, where we start the research at 40 and we go up to 100. So people are less confident about the research, more confident about the research. And what we have here on the y-axis, this is the score you got on the pretest. So I asked you a series of what are called didactic questions. They're sort of fact-based questions. They're not thinking logic questions. They're just, here's some information. What is the correct answer? There's a right answer, there's a wrong answer. And this is your score. Or both, you know, relative to statistical intuition and relative to research skill. A lot to unpack here. What you're looking at here is you're looking at a best fit line, okay? And this gray area is what is called a 95% confidence interval. And we'll talk about this in detail later. But this is the range in which that slope could be. So this slope could be steeper down, but the slope could be positive. So it could be even more negative than we actually measured, or it could actually be positive. These are results of what are called a permutation test, which I love. Permutation tests make me so happy. Don't worry about it today. Not a big deal. We'll talk about it later in the semester. But I will take you to sort of some of these values. And the only thing I really want you to focus in on is the R squared. The F test, the degrees of freedom, p-value, you may remember that. But the R squared describes how strongly related one variable is to another variable. So an R square of 1 means that you can predict the y-axis, the value in the y-axis, if you know the value in the x-axis. They are a perfect match. So if I told you what the x-axis is, you automatically know what the y-axis is. They perfectly relate. A value of 0 means there is no relationship at all, none whatsoever. Means that if I tell you what the x-axis is, you do not have any confidence in saying what the y-axis is. Make sense? There's lots of stuff to unpack in these figures. So I'm going to start with Cortland. What do you see, buddy? Give me one thing, just one thing.
The R squared value for statistical intuition is lower. So that means that like your perception of your own statistical intuition had even less to do with your score on the pretest, which was a lot of statistical recollection.
Yeah. No, this is all facts-based stats. This is not thinking stats. It's just facts-based stats. But the R squared value is basically 0. Is there any relationship between your self-confidence and your score?
No.
Okay. And Riley, if we can follow up on that same idea, with this R squared, is there any relationship with your perception of research skills and your statistics?
Not really.
No. And research requires stats. I mean, it's the most universal tool in science after writing. Writing is the first most important tool, being able to write, communicate. The second most important thing is statistics in order to do research. So, right? Morgan, what else do you see?
I'm sorry, can you repeat the question again?
Yeah, just what else do you see here? So one thing we saw is that there's no relationship between your self-perception score and the score you got on the pretest. No relationship. If you're really confident in research, that had no relationship to your actual score. If you were really unconfident in terms of your statistical intuition, that had no bearing on your actual score. What else do you notice about these figures?
I noticed that, let me see. I noticed that people were also more confident in their research skills than their statistical intuition overall.
Yep, you guys are definitely more confident in research skills than your statistical intuition. Yep. Anything else we noticed in these figures? Oh, this one's open. Morgan, your answer was perfect. You're not required here. And this one, I'm just going to open it up to the peanut gallery. Is there anything else that someone noticed here?
They look the same.
They're very similar. Yeah. They're very similar. The slope is almost exactly the same. The R squared values are almost exactly the same. How did you all do on the pretest?
Not great.
Not great. No, not great. But there's two caveats. No one got a 0. No one got 100. And what should that tell you about this class?
You have a chance.
We have some knowledge. Yeah.
You've got to start it. You've started somewhere. We got a little bit of foundation. That's good. What else does that tell you about this class?
There's still a lot to learn.
There's a lot to learn. You should be in this class. Welcome to Biological Statistics and R. As we go through the semester, there are times where you will be challenged and where you'll be frustrated. I promise you that we will get past that. In the beginning of the semester, especially when we start playing with some initial R, and when we start sort of playing with what stats do for us and what they do not for us, a lot of you will be annoyed by that and sort of find it painful. Not a problem. I also promise you by the end of the semester that this is very likely going to be one of the more rewarding experiences that you have. You will not come out of here as an expert in biological stats. That's not the point of the class. What you will get is a good foundation that you can then build on. But as we're about to talk in a few minutes, stats are shockingly frustrating. They were frustrating for me when I began. They can still frustrate me immensely. But they truly are one of the most powerful tools that we have available to us. So some of the things that you guys talked in terms of your qualitative, and while this is not a qualitative data analysis, I do a lot of qualitative data analysis, and I thought it was important to sort of include your words. Some points of biological statistics, pattern recognition, you guys described that earlier, but that was a very good observation. The tool in research, no question about it. The ability to test hypotheses. And one of the things I didn't see, but is really true as well, to formulate hypotheses. And one of the things you guys did as we looked at these data is you started formulating hypotheses. That's a very important tool of statistics, and you did a very good job with that. Make predictions, absolutely. But I also really enjoyed this last answer. I don't know. That's fair. That's what do a lot for us. It doesn't do everything for us. It does incredible tool, but there's more that can be done with it. What do you hope to get out of this class? Great in understanding. Yeah, sure, an A. I think it's a great sort of goal. And to better understand how to interpret data. Excellent. A lot of people put down things about understanding an R. I thought this example was a really good one. I hope to gain a better understanding how to use statistics properly. I also know that learning how to use R and get more experience at working with Excel can do nothing but benefit me in my future career. And people will use the skills they develop in this class in a wide diversity of ways. Some have taken it into their medical practices, and they've sort of treated their medicine in a more quantitative fashion than is normal for MDs. Some people have gone into law with this class and sort of taken on law with more quantitative approaches. I've seen some students go into business with this, and then of course students go into research, and they go on for masters and PhDs, but it can be applied very broadly. A lot of people talked about research, and I thought that was great. I'm excited to gain an even better understanding of R and statistical concepts in general to the point where I can use them comfortably for my research. That's brilliant. And on that note, if you want to use some of your data in this class, please. We can either use it as part of the things that we learn in the class, or sometimes I've been asked to use it as a test question. Happy to do that. Or if there are things that you want to play with in terms of your data and sort of gain some additional insights, we can base it on what we do here, and then we can talk to you outside of class. And Dominic is actually a good example of that. He wanted some extra help to sort of play around with his data set that he was doing in terms of his research. And then this is very true, career. I like this example. I hope to gain valuable experience in coding and statistical analysis, better prepare for my career. And that can be highly variable. And if you know how to use data and you know how to analyze data, you really have an incredibly unique and valuable skill set that can be used by any variety of individuals, including careers that you decide to create. So you're not actually taking on someone else's job, but being more entrepreneurial with the type of things you do next. Describe some exciting moments. I loved my professor that I had for mathematical stats. I thought that was awesome. If this was you, I would love to know who that is. Oh, I don't know what's going on here. Okay, so here we go. Experience in research. I'm currently working on a research project where I'm analyzing group behavior. I think that's great. I passed the class. It was my first semester in college. I was nervous. I had success. That's good. Future, understanding the lottery system. Well, if we could all understand the lottery system, we would be quite happy. We would also be pretty poor because we would be splitting it up so many different ways. But I got a lot of these too. Either they were blank, or my favorite was Mm. So those were good. Those were good. So, there's a typo in this question, but I'm not sending you out to answer it anyways. Why are statistics difficult? Why are they non-intuitive? Well, I want you guys to sort of give initial thoughts. Sort of, are stats easy? Are they too intuitive? If so, why? If not, why? And what you're looking at here are the equations that Fisher created when he invented an ANOVA test, the analysis of variance test, one of the sort of standard introductory procedures. And it's a really good representation of some, what would be called good introductory stats. So I'm going to give you guys about maybe, 5 minutes. Are statistics easy and intuitive? And whether you say yes or no, why? See you in a bit. First, the other side without question. Yeah. I would give one at least 1 or 2 and 3. There's going to be someone in that group. There's always.
Billy, can we get a break soon?
Yeah, take it right now.
You sure?
Come on, yeah, come on back at 4:40.
Thank you.
All right, why don't we go ahead and get started again? I'm trying to go into the chat and respond to questions and comments that came up. And if I miss something where you have made a comment or have a question and you're not getting a response back after a break, just resubmit it or re-ask it. A lot of your questions that were put into the chat, don't hesitate to ask them of the entire group. One, someone in the class may have a good answer or response to it. And you will be a very valuable tool for each other throughout the semester. So don't hesitate. And then two, we're all starting on very equal and good footing. We've got a lot to learn. And that includes me. I mentioned it on Tuesday, but I didn't mention it to be pejorative. I mentioned it because it is reality. I spend a significant amount of time continuously learning more about my science, my statistics, my research, my teaching on a daily basis. I do not assume I have good knowledge. Instead, what I've gotten very good at is ways of learning and ways of getting additional information, additional skills, so that I can apply them to new and novel situations. Well, I'm going to pick on you for a half a second. You and I were looking at some sound files today because I'm kind of interested in some audio research, and I don't have necessarily good answers in regard to that. I think that's exciting because we're going to have to try to figure out what to do with it and how to do it. But it's very little about memorization. It's a lot more about thinking through the challenges that are there, and that's a lot what we do here. So I asked a question, but I don't think I'm sharing with you right now. So let me share.
I can see it.
You can see it. Thank you.
You're welcome.
I don't know if we're recording or not. So we'll resume. Okay. Stephanie, are you with us?
Yes.
Oh, welcome. Good. So I'm gonna hit you with this question. Are stats easy?
So I would say yes. Like, it's pretty straightforward, but to me personally, like, once it's like, formulas are straightforward, but once the numbers get involved, I feel like it gets more complicated.
Ooh.
Like, for me personally, but yeah.
I think
So yeah. So I think I think it's easy, and like when I remember learning it, because everyone told me like it's the hardest class in college. Like, either you fail it or you're really good. And I remember taking it, and it was pretty easy. I didn't see how people like failed it or did so bad. But then now looking back, I'm like, how did I do that? I don't even know what I was doing. I don't remember how to do that. So I don't know.
Oh, yeah. Interesting. I like a lot of that. So there can be elements that we find very easy. There are also elements that we're going to find particularly challenging. If you do find statistics challenging, I think you're probably in the house with most people. And that would definitely include me. Humans do not think statistically. One of the pieces of evidence that I can provide for you that sort of reinforces that point is the sort of modern use of statistics is only about 100 years old. And I mentioned that briefly on Tuesday. I'll probably mention it 2 or 3 more times throughout the semester, but try to digest that for a half a second. The modern development of science is more than 500 years old. The modern application of statistics, which is one of the reasons that science has just exploded over the past 100 years, is about 100 years old. This is an ANOVA test. ANOVA test is one of the most important introductory tests around. That was invented in the 1930s. Same time that we were making that connection between genetics and evolutionary biology. That would be the modern synthesis, which all of you have basically sort of grown up in and learned through. Now, process that. We've lived in cities for more than 10,000 years. Agriculture, 7,000 years. Statistics, 100. We're not prone to stats, but I really loved what you said. Some parts we may find pretty easy. One of the things I hope that you learn throughout the semester, and we will practice it, is how to read a mathematical equation the same way you would read a sentence. If you try to memorize variables and what the numbers and letters mean, that's really difficult. But if you get a key that tells you what the variables are, then we can read them much like we read a sentence. And if you can start to read them like you read a sentence, then the logic that is going on underneath them starts to make a little bit more sense. Once you get the logic, then you get that part that was just being discussed by Stephanie, and that is what those numbers start to actually mean to you, because we report these weird numbers. I think I showed you, yeah, a good example right here. We'll go back. Yeah. You know, linear permutation test, F. What the Hades does that mean? DF, 1,24. What does it mean and why do you have to show it? P. P is one of the most inappropriately understood concepts in biology and chemistry and physics and geology and environmental science and basically all science. R squared. All these are random numbers. They have logic. And part of what we'll try to do is get at that logic. But if you feel challenged in sort of getting at that stage, don't worry, that's being human. In order to learn stats, you have to reframe your thinking. And I'll sort of show you a few illustrated examples. And statistics are our tool for quantifying and describing patterns. And I cannot overstate how important that has been to the revolution that has gone in science over the past 100 years. It is shocking how much we have learned and how much we have discovered, primarily because of the ability to apply statistics broadly, appropriately, and therefore understand patterns that otherwise would be obscured. It is not straightforward. We do not think statistically. Some proofs of that. We have a lottery, and it is a self-funding mechanism to which we can derive profits from it and use those profits for other efforts. If humans understood statistics, there would be no lottery. It makes no sense statistically, unless you enjoy adult play where you spend $1 on a lottery ticket and then you just play, what would you do if you had this much money? And that's fine. That could be a good evening. We would have no casinos if people understood statistics. They wouldn't exist. Because we don't understand odds, we can have casinos where people are very happy to just give away their money. Now, if you want to go in with 20 bucks and you just walk out knowing you're going to have zero afterwards, that's awesome. But that's not how casinos operate. They don't operate on that. What they operate on is the person who's going in there, the next one's going to be my winner. And they put down the extra money. There would be none. Yogi Berra, the catcher for the New York Yankees back in the 40s and the 50s, freaking brilliant. If something has a 50% chance of happening, then 9 in 10 times it will. This man understood stats, and he made jokes with them. Baseball is 90% mental, and the other half is physical. Like the phrase, have you ever heard the phrase, give 110%? If you've heard that phrase, and you've said, okay, I get it, that doesn't make any sense statistically. Statistics are a different way of thinking through something. You give 100% in the first half of the game, and if that's not enough, in the second half, you give what's left. Which is 0. Thank you. In order to do statistics, you have to be trained. In order to do statistics, much like science, you have to be trained. We as humans, we're great at making questions, but that doesn't mean we're good at science. In order to do science, you have to be trained to think a particular way, to take out the subjectivity as much as possible in order to address and analyze questions. And that is not an easy thing to do. Statistics operates in a very similar way. Start here. And for this one, I'm going to ask Ben Hassel. Which population is at greater risk of pharynx cancer?
Well, you're making me do quick math here.
I am making you do quick math.
I'm not good at quick math. I'll say male. It looks like a 1 in 10. The other, not so much.
You know,
No.
actually, and I really appreciate that. So let's actually recognize what you did, Ben. Not getting the math correct is much less interesting than what you did. And that was, you recognize we actually have to evaluate a ratio. So who is more likely to get pharynx cancer? If these are random samples of the population, that's male. Males show the cancer in 10,000 individuals in a comparable population, only 3,000 females show it. But once you get it, who's more risk at death? Then that actually becomes females. What you did was exactly right. So I would give yourself full credit there. You recognize that looking at the number is not really the issue. Looking at the number relative to the population is the issue. But it's always looking at the number. So who's more at risk of getting this type of cancer?
Females.
Males.
What?
If you get this cancer, who's more at risk of dying?
Females.
Females. So this is kind of like what we were looking at that first graph I was showing you. The graphs in these data give you certain information. They also do not give you other types of information. So just knowing the number of people who develop the cancer, that's one type of information. Knowing the ratio that die as a result of it, that's a different type of information. What we want to do in statistics is we want to look broadly across all of those issues. Otherwise, we get confused. Okay, so we have enough time for this. This makes me happy. Get out a scratch piece of paper, or type it on your computer, or keep a note. But you need to write it down somehow, either by paper, by pen, on your phone. I don't care. So what I'm going to do is I'm going to give you a bunch of factual pieces of information. These are sort of numeric statements that have a correct answer. What I want you to do is I want you to put down a range that represents your confidence. Now, you're going to be 90% confident. The true answer is within that range. Make sense?
Not really. Could you go over that again?
Sure. I'm going to give you a statement like, how old am I? That has a factual answer. What you would then do is you're going to put down a range that sort of represents your 90% confident. So maybe you're 90% confident I am somewhere between the age of 72 and 74. Or you're like, no, I'm 90% confident that he's somewhere in between the age of, I don't know, I'm not really sure. I'm going to say maybe somewhere between 25 and 75 because I really have no idea. So you put down the answer that represents your degree of confidence.
Okay, gotcha.
Does that make sense?
Yes.
Okay, so you cannot cheat. How can you cheat?
Googling it.
You can put down 0 to infinity. That's boring. Don't be boring. No boring people allowed. I want your degree of confidence for each one of these things. We got it? Make sense? Questions? Okay, so please put down the age at which Martin Luther King Jr. was assassinated. How old was this man when he died? And put down a range. If you are 100% certain, you could just put down a number. Put down a range where you are 90% confident his age at death is within that range. You all ready? The length of the Amazon River in either miles or kilometers. Obviously, you should put down kilometers, but we're from the USA, so miles are fine. The length of the Amazon River. From its origin in the Andes of Peru to its outlet in the Atlantic Ocean.
Dr. Gunnels, any of the tributaries or the headwaters included in that?
Just from the origin, the straight Amazon. So no Orozco, no Negro, just the Amazon.
But what about the indigenous people of the Amazon who believe that it is really the birth spring of the waterfall 3,000 miles inland that is the true start of the Amazon River?
Okay, we can discuss that afterwards. We're just putting down our answer now. Put down your range.
I'm gonna say 2,500 miles.
No, not out loud, write it down. Oh. All right. The number of nations in the Caribbean.
Now, what defines a nation, Dr.
Okay, so I'm gonna either give you I'll give you both nation as well as dependency. So you can put down either one of those two answers.
Like a territory?
That's a dependency. Yeah, so you could either one of those two answers, but put down whether you're doing nation or nation and dependencies. So as an example, Puerto Rico is a dependency. Cuba is a nation. Puerto Rico is a territory, part of the United States. Cuba is an independent nation. So whichever one of those do you do, put down nation or nation independency and give your range. Number of feature films directed by George Lucas from Star Wars fame. Yes, the guy who built the Imperial Star Trooper that I see in the clouds. But not right now. I don't look at the clouds. The distance of the sun to the earth in either miles or kilometers. So far there have been 5, we'll have 5 more. Age to which Martin Luther King was assassinated, how old he was, the length of the Amazon River in miles or kilometers, the number of nations in the Caribbean, number of feature films directed by George Lucas, distance of the sun to the earth. Okay, number 10, because I don't know how to set up a PowerPoint. The tallest tree from its base, not the roots, from the base to the tip, the California redwood, in either feet or meters. And for these where you get to decide the units, make sure you identify the unit. The number of Boeing 737 planes that have been sold, and this is as of last year, prior to COVID. And this is the most common passenger plane on the planet. The year.
New ones or used ones?
New, just new. The year Socrates was born. Number 7 is the year Socrates was born. Number 8, the average gestation period of a sperm whale in days. And then number 9, the height of Mauna Kea, which is the large volcano on the big island of Hawaii, from its base at the bottom of the ocean to its peak, in either feet or meters. Number of sold Boeing 737, year Socrates was born, gestation period of a sperm whale, the height of the big mountain on Hawaii, and the height of a California redwood. So, this is an issue of confidence. How many questions were you asked?
10.
You were asked 10. Okay, if you give a range that represents your 90% confidence, how many answers should you be correct about? You were asked 10 questions.
9.
You gave a range of 90% confidence. You should be correct 9 out of 10 times. So the true answer should sit within your range. Does that make sense? You know, randomly, maybe you'll be only correct 8 times because there's a little random variation. And maybe you'll be correct all 10 times because there'll be a little random variation. But on average, if you show something 90% confidence, you should be correct 9 out of 10 times. Questions? Okay, so what I want you to do is I'm going to give you the answers. And I want you to identify with a check when you are correct and an X when you are wrong. So when your range sits within, the true answer sits within your range, that's a check, you got it right. When the true answer is outside of your range, that is an X, you got it wrong.
I wanted to ask, what was number 9?
Oh, I'm about to show you. We're going to see it again.
Yeah.
It's the height of the big volcano in Hawaii, from its
Okay.
base in the ocean to its peak. So Martin Luther King Jr. died at the age of 39. I'm 49. I find this embarrassing that I have done so little in my life relative to this man. He was 39 when he was assassinated. I gave you the wrong one. I will get the Amazon in just a half a second. I wrote that. Anyone wants to look Amazon River because I put that in correctly. The Amazon River is 4,086 miles. Or 6,575 kilometers.
So it's almost as long as the Mississippi River.
Yeah, that's wrong. I screwed up this one. So we're going to say you got 8 out of 9. We're going to skip number 2 because that's wrong. I think this is the Amazon. I don't think I put it in the Mississippi. I just think I left that as a typo. Let's move on to number 3. The number of nations in the Caribbean. There are 13 separate nations, and there are 25 nations and dependencies, which include things like Cayman Islands, Puerto Rico. The number of feature films directed by George Lucas is 6. He was involved with a lot of other films, but he only directed 6 of them.
Did he not direct American Graffiti? I thought he did.
I think he.
That must have been.
I think that's actually one of his.
But like a Spielberg thing.
It might have been Spielberg.
Oh.
But that's
when it was like he co-directed. That's crazy.
He doesn't have many.
Yeah.
The distance of the sun to the Earth in miles or kilometers: 93 million miles, or 150 million kilometers. So for each one of those, except for the Mississippi, Amazon River, identify whether you got it correct or not. The number of sold Boeing 737s, almost 15,000. 14,956 airplanes have been sold. New airplanes. The year Socrates was born, 470 BCE, or 470 BC, however you record time. Average gestation period of a sperm whale, 535 days. Almost 2 years. That is a very long pregnancy. The height of the big mountain on Hawaii is 33,479 feet. Remember, much of that is under the ocean. So it is the tallest prominence on the planet, taller than Everest from its base to its peak. But much of that is on the ocean, under the ocean. And then the height of a redwood tree in feet or meters, 379 feet is the tallest redwood we know of, 115.5 meters. More than a football field. Huge. So far, so good? Okay. So, add them up. How many answers were within your range? In this case, the perfect score would be 9. We would expect 8 if you did your 90% confidence. So, using the emoticon, which you can find at the bottom, put your thumb up when I ask for a particular number. If you had 9 out of 9 or 8 out of 9, please give a thumbs up. Go Mitch. Go Tristan. All right. If you had 7 out of 9, put a thumbs up. We got Dakota. We got both Dakotas. That's and Ipti. Excellent. How about 6 out of 9? All right, we got a few more. And you go ahead and put your thumb down at this point. How about 5 or less? When we do this nationwide, American students end up getting about 30% correct. What does that tell us about our ability to estimate numbers? Or what does that suggest about our ability to estimate numbers? Students from the US nationwide get the correct range about 30% of the time. 70% of the time, they do not report the correct range. What does that suggest? Tristan?
Either we don't know enough about physical science to like really estimate the world around us, or what was I just thinking? People do their ranges too small and hope that they'll nail the figure, when really to be 90% confident, like if you were going to bet money and you wanted 1 to 10 odds, would you be willing to bet on that you'd get your money back 10 to 1?
Yeah, those are two good explanations. What else do people think? This is a pretty strong universal. When we do this, and we do this all the time, US students about 30%. Different countries a little different, but what we never see with people is 90% confidence, unless they've had some experience with this. If someone asked you, go ahead, I'm sorry, who's that?
Maybe people are bad with scale.
Scale. We tend to be overconfident in our knowledge. Right across the board. We tend to be very overconfident in our knowledge and understanding. Both mathematically, as this case, but in other facets. There's also kind of increasing reinforcement. If someone asks you a question and you give them an honest answer where you are 90% confident, how big of a range is that going to be? Is it going to be big or is it going to be narrow?
Big.
It's going to be big. Try doing it. Try giving honest answers when someone asks you a question. You know, how old was Martin Luther King when he died? I don't know, maybe somewhere between 25 and 70. What are people going to do if you give them an honest range?
Not ask you questions anymore?
Not ask you questions anymore because they don't think you know anything. So one of the things we do is we police each other to really give inaccurate ranges, but ones that make us look confident. So there's a host of reasons behind this, but this is something that we're always challenged with. And if you really want to try for a while, try giving honest answers in terms of your confidence in the range. When you're certain the range is going to go down. When you don't really know, like the gestation period of a whale, well, without reading it, I don't know. I'm assuming probably somewhere at least comparable to human. So 200 days, maybe a little bit less, because maybe it's faster. So maybe 100 days, but it could be really long. I don't know. How long can an animal actually be pregnant? Maybe a year? That seems crazy. My reasoning would be obviously wrong because their gestation period is much longer than that. But try to give some honest answers and pay attention to how people respond to you. They will be annoyed. Do one more example. I can actually get to the screen. Shaquille O'Neal. We're back in the NBA. If you like sports, this is a reference you might understand. If you do not like sports, let me tell you a little bit about Shaquille O'Neal. First, the guy has the biggest shoe I've ever seen. It's a freaking monster. It's an enormous shoe. He is a center in basketball, and he was one of the most dominant players of his time period. He's still very famous as a celebrity because he also has one of the most affable personalities, and he just seems to show up and everything because, well, just a good guy, or at least he projects being a good guy. He was dominant on the court because he was also huge. You know, I mean, I'm not big, I'm small. So most people by my standards are huge. But for a basketball player, they tend to be enormous. And they would stand next to Shaquille O'Neal and they would look like little toothpicks. And what that meant is Shaquille O'Neal wanted the ball, he could just push you and you're off the court because, well, you're tiny by comparison, and the guy is just huge. He dominated every aspect of the game. He had incredible shot records. He could get right underneath the basket and just destroy anyone who tried to come in. He was famously, or in this case, infamously, a terrible free throw shooter. And in the game of basketball, go ahead, what?
Sorry, there was just some.
Okay. In the game of basketball, free throw is considered a sort of a simple exercise. It's based on just practice. And the more practice you do, the better your free throws should be. And a professional normally is somewhere between 75% to 90% accuracy in terms of their free throw. So when they shoot, 9 out of 10 times they make it, maybe 7 out of 10 times they make it. Shaquille O'Neal, it was about 50-50. They shoot, sometimes you make it, other times not at all. What you're looking at here, going across, is his successes out of 100 shots. If it has a dash, that means he shot it and he missed it. If it has an X, it means he shot it and he made it. And this would be the first shot, the second shot, third shot, fourth, fifth, sixth, seventh, eighth, ninth, 10th, and then the 11th. This would be the 21st shot, and this would be the 100th shot. One of the things that people have talked about in sports is streaking. The idea that if you do something successfully, that is going to increase the likelihood that you do it successfully again. And what I want you guys to do is take a look at this and see if you see any streaking patterns. And this one's just open to the peanut gallery. Say yes or no whether you see something. It looks like it's streaking.
I see there's 2 points where he made 6 in a row.
Ah, we got a point down here where he makes quite a bit in a row. We have a point right here starting at the 49th shot, 50th through 54. Yeah, that's interesting. Anyone else?
When you look for the patterns, you see them.
When you look for patterns, you might see them, and you might see them in the negative as well. So you may see periods where we don't see a lot of baskets being made in a row. So streaking normally describes positive, but of course it could also be negative. Anything else we see?
Is this the guy in the Papa John's commercial?
I have no idea. Is it Papa John's commercial?
Yeah, I think so.
Okay.
He's in like every commercial.
He's famous.
I think he's on the general commercial.
He does the general, yeah.
That's
oh,
it.
thank you. Thank you. We know.
Super famous now.
It's good that he's still being paid. So
Yeah.
some examples of where we might be seeing streaking, and like you have a salon case where you get mostly made with a few misses overall. We tend to see patterns, and this is sort of Mitch's point that he was bringing up. Streaks are there. Whether they're there because of real biological, sociological reasons, that's unknown. In this case, this table is just created randomly, where each one of these are random numbers. If the number was above 0.5 on a scale from 0 to 1, it became a made. If it was below 0.5 on a scale of 0 to 1, it became a negative. And even that, kind of like flipping a coin. Can you ever get situations where you get multiple heads in a row? Does that mean that the coin is cheap? Maybe not, maybe yes. Can you ever get them where all tails in a row? And again, maybe yes, maybe no. Now, if you flip a coin 10,000 times, and 9,000 out of those 10,000 times, it comes up as heads, is that a cheap coin?
Yeah.
Oh, yeah. Oh, yeah. But if you flip it 10 times, and 7 out of 10 times it comes up as heads, that could be completely random. I'm going to highlight these two papers. I'm going to stop here. This idea of streaking and whether streaking really occurs, if you are interested, is one of the more hotly debated topics in science. And it was a paper that came out a long time ago that said streaking is a completely random event. And then 3 years ago, there was a follow-up to that that actually provides pretty strong evidence showing that while streaking is not exact, you do see an uptick of about a 2 to 4% increase likelihood of success after a successful period. And that's not a huge chain, but it is a significant chain. Both of these papers are on Canvas, if you want to take a look at them. They're not required, but they are optionally available. If you have any questions, stick around afterwards. Otherwise, guys, have a great weekend. I will see you next week. Mitch, if you hold on for 2 seconds, I'd appreciate it.